strategies using maximally entangled states, and the talk is being given by Paddock.
Is there a way I can get rid of this window here? Does anybody know? Okay, thanks everybody for joining my talk. I'm going to be talking to you guys about a result about non-local games, taking near optimal strategies and looking at how you can turn them into strategies where you play with a maximally entangled state and still get something that's close to being optimal. So first I'll go over a little bit about non-local games for those who aren't experts, and then I'm going to talk a little bit about algebras and how they interplay with non-local games. The type of non-local games that we're interested in this talk are two-player non-local games where there's two players, Alice and Bob, and they share a bipartite quantum state on a tensor product of Hilbert spaces H, A, and B, and a referee gives them input questions I from a set I, J from another set J, and they respond with answers A and B. And the referee then determines whether they win or lose based on a function or a rule predicate that's denoted by V. So what's a quantum strategy for a non-local game? Well, it consists of a set of, first of all, it's a pair of Hilbert spaces and a set of measurement operators which the players employ based on the input they're given. So you can see here that they have a collection of projective valued measures for each input question on their local Hilbert space. And similarly, the other player as well has one of these collections. And the reason here that I'm just looking at projective strategies is that whenever you have infinite dimensions of POVM strategy, you can dilate that to a projective strategy with a pure state using some standard dilation techniques. And because we're in finite dimensions and we're just interested in those correlations, it's okay to restrict to those ones. We're also going to need the value of a game, which has fortunately been discussed before. But here I'm going to talk about the value of a game with respect to a specific strategy. So here, the value of the non-local game with respect to the strategy S is given by this quantity here. You see the quantum correlations on the right-hand side of this expression, where the bipartite separation of Alice and Bob's measurements appear. So really, the local observables they're applying are tensored with the identity on their part of the space. We've also seen before that the value of the game is then the supremum over all of these types of strategies here. And we denote that by omega star of G. And we say that a strategy is optimal if, of course, the strategy with respect to S achieves that value. We're not saying anything about the uniqueness of that strategy here, just that there are these optimal strategies. They're the ones that attain this value. So what are some types of non-local games, and what are the non-local games that I'm interested in and apply to this talk? Well, a large class of non-local games that have garnered a lot of attention lately are the synchronous non-local games, and they're very nice. In a synchronous game, the input and output sets for each player are the same. And in addition, whenever the players receive the same question, they must reply with the same answer. So this is what this expression here says, that they lose basically whenever they give different answers to the same question. And a wonderful example of a synchronous non-local game is a graph coloring game, where the players are given a graph, G, and the referee gives them vertices in the graph, and they need to color the graph in a way that no two vertices have the same color and no two adjacent vertices have the same color. So of course they lose if they ever assign adjacent vertices the same color, and given the same vertices, they obviously need to give them different colors as well. Yeah, so that's where the synchronous condition there is coming in at the end there. Another type of game that's very interesting is called the binary constraint system game. Here you have a system of Boolean constraints. So you might have a bunch of Boolean formulas that describe your constraints. These formulas might include a list of variables. And the way this game works is that one of the players is given one of these constraints, and they must reply with a satisfying assignment. So a set of variables that satisfy the constraint. So you can think of these as being kind of like 0, 1 value Boolean constraints here. And there's some system of them, and they're just given one of them. Meanwhile, the other player is given a variable, a single variable. Often the distribution on the questions is picked in such a way that they're given a variable that's in the scope or the involved in that constraint, right? A constraint might not contain every single variable on the system. So the game is sort of trivial when, when they're asked about variables that aren't even in the constraint of the first, that the first player is given. But either way, they're kind of given that a variable and they need to reply with a single 0, 1 or plus minus assignment to that constraint. And they win if and only if their assignments are consistent. So if the jth variable in Alice's assignment is exactly the one that Bob gave to. And a lovely example of this game that has a really nice juxtaposition between a perfect quantum strategy and no classical strategy is the Mermin prismatic square. I've written the constraints multiplicatively here. So these xi's here are going to be plus or minus 1s. So Alice is given a constraint, 3 variables that need to multiply to either plus minus 1 given the constraint CI. And Bob is just given a single xij here and must decide at plus minus 1. And they lose if their assignments will differ. So of course, you might have seen this magic square before where you know that you can't find a assignment to all the variables in the 3x3 grid, but you can kind of have this quantum way of a quantum satisfying assignment, if you will, for these variables. Another very prolific class of non-local games are the XOR games. In the XOR games, you just have inputs to the players, but each player just replies with a single bit. And the winning predicate for this game is just based on a function of their inputs. And they win if the XOR of their output bits is equal to the value of this function, which they know. The classic example is the CHSH game, where each player is given a bit and they respond with a bit. And the function here is just the AND of their inputs. So now we're going to kind of switch gears a little bit. I'm going to tell you about algebras because the point of this result is to kind of talk about the interplay between algebras and non-local games, which is recently come to fruition over the past decade almost. So what are the types of algebras I'm interested in here? And they're the finally presented algebra. So a finally presented algebra are a unidal complex finally presented algebra with a star. So I have a convolution here, like a conjugate transpose, is a set S. So you have a set of indeterminates or your variables, and then you have a set of relations, which are just star polynomials in those relations. And the finally presented algebra, I've written here C star and then in brackets S colon R. It stands for the free algebra generated by S modulo the star ideal generated by R. So this is the smallest two-sided star ideal containing all of your relations. And we'll see several examples of these and how they arise from games next. But before we get there too, I want to mention what a representation is. So a representation of a finally presented star algebra is a mapping from the set S to the matrices, well, from this free algebra C star S to the matrices such that all the polynomial relations are 0. So here R is standing for all the polynomials that I have above. And so if all these polynomials are 0, then they're in my ideal and I have a representation. So this is just a homomorphism, right, to the matrix algebra. I'll mention too that up here when I have S and R, those are what we often refer to as a presentation of an algebra. So we've seen a synchronous game. There's an algebra associated to the synchronous game called the synchronous game algebra. And it has indeterminates PIAs. And the algebra relations here are that they must be orthogonal projections. They must sum to identity. So right now I'm saying basically that these need to be for all, well, I have an X here, that should be an I. But for all the inputs here, I have a bunch of projective measurements basically. And the last relation says basically what I want all of my projections to do if I have a perfect strategy for the game. So if the rule predicate is 0, then I want the corresponding projections to be orthogonal. So for those input questions or inputs, I want their output projections to be 0. And you may wonder here, well, where's Bob's algebra it looks like just like you have one set of measurements here. And an important feature of all the games I'm looking at, and these results seem to hold for, is that essentially what happens is that one of the player strategy almost fixes the others. And this is an important feature of these types of games we're looking at, and what makes going beyond them in an algebraic setting quite difficult. So like for a synchronous game, there's also an algebra for the BCS games, and these are a little bit different in flavor. Typically, we express the BCS game algebra as a bunch of, instead of projections, we talk about them as being self-adjoint observables. And this is just a transformation that we can make between them. In fact, for a synchronous game, we can also, it's also isomorphic to an algebra that's generated by these, unitary or plus or minus one valued observables or self-adjoint unitaries. And it's just convenient to write them in this way because we'll see how, they're more akin to the kind of assignment variables that we see in the classical case. So I need the elements of my algebra to be plus minus one of valued observables, and I also need them to satisfy all the constraints. So here, the fi's are basically the polynomials that I get. They're multilinear real polynomials that I get from taking my constraints and kind of moving them from ands and ors and xors into the language of real polynomials, which I can do using some kind of just Boolean algebra kind of techniques. Of course, these fi's are, they need to be, the variables within these constraints need to be commutative. So the algebra itself isn't commutative, but for each constraint, if for any pair of variables that appears in that constraint. So here I've written fi has x1 up to xn, but it might only include kind of x1 up to xk. But those variables need to commute within the constraint. The next algebra that we associate to our games is the XOR or solution algebra. And this game involves something called the cost matrix and the marginal row biases, and I don't want to worry about those too much, but they just come from the description of the game, the probability, and that function I talked about, Fij. The point here I want to make is that there's a representation, or there's a presentation of the XOR game as a finally presented algebra, and all of the optimal strategies, well, as we'll see, there's an algebra associated with this, and I'll get right to the punchline, is that for all these games where I've mentioned, there's finite dimensional quantum strategies and there's representations, I have the following equivalents, that optimal finite dimensional quantum strategies are equivalent to finite dimensional representations of these game algebras along with a maximally entangled state. So if you're at Hamoon's talk the other day, he talked a little bit about this, and he was asking whether, what happens if we have near optimal strategies? Do we have some sort of near representations? And that's exactly what I'm going to tell you guys about today. So what I want to do is I want to look at this course. I want to ask whether this correspondence is robust. So if I am no longer a optimal quantum strategy, or I'm no longer exactly a representation, do I kind of fall off the map, or do I still stay close? Do I still say poly epsilon away from in either case? So before I do that, though, I need to talk about what does it mean to be a near optimal strategy. That's not too hard. And then a little bit more difficult, but nice mathematically, is I need to tell you what it is to be a near representation. So like I mentioned, describing what a near optimal strategy isn't that hard. It's just whether your strategy is epsilon away from the optimal value. A near representation, though, is a little bit more daunting of a task to define. But if we recall our definition of a representation before, it's not too bad. Basically, an epsilon representation is a map from the free algebra C star of S to the matrices, where instead of the polynomials being exactly 0, I put some norm on the matrix algebra. I can do this. There are lots of nice norms on matrices. And I demand that, well, I find the epsilon for which all of the relations are bounded by. So I take the smallest epsilon for which all these relations are less than epsilon in that norm. Now, this is a notion from something called approximate representation theory. And it turns out that the choice of norm here is actually very special. All sorts of interesting results. You'd think that maybe you pick one norm and everything's the same, but lots of interesting stuff happens. So you need to talk specifically about what kind of norm you're talking about here, because it does matter. And you can study approximate representation theory in pretty much any kind of norm here, or you could talk about other algebras as well, not just the matrices. So the norms that are important for us are these so-called state-induced matrix norms. And everybody knows that everybody's favorite norm maybe on the matrices, at least mine is the Hilbert-Schmidt, or the norm inherited from the Hilbert-Schmidt inner product, the Hilbert-Schmidt norm, or the Frobenius norm here. It's just the square root of trace of A star A for a matrix A. And but I'll note that if you have a density matrix here, so that's you know, a trace 1 positive semi-definite matrix here, I can get a matrix semi-norm by kind of just sticking this row into my trace here. And this is actually, it's a really nice norm. The only reason it's a semi-norm is if row is kind of rank deficient. So as long as I kind of restrict all my operators to be in the span of my, or in the support of row, then this norm will actually be a proper, the semi-norm will be a proper norm. I'll just note that if I take the maximally mixed state, which is kind of an important density operator here, I get something called the little Frobenius norm. And this is actually our favorite norm in this thing, because it's unlike the Frobenius norm, the little Frobenius norm is unital, so it takes the unit to the unit, or it takes the unit to 1. And it's sort of natural in the sense that, as we'll see, you know, if we're looking at representations where the state here comes from the strategy, maximally entangled states, we remember, have reduced density matrices that are proportional to the are of this form, and so it's a natural norm to talk about kind of one inherited from entanglement, or maximally, the notion of being maximally entangled. So what are the key observations here for near optimal strategies? It's right off the bat. I'm not going to get into proving these things. But as I mentioned, if you take the reduced density matrix of the state employed by Alice and Bob in their strategy, and you look at the reduced density matrices on Alice or Bob's side, then I get this induced row norm on their measurement operators. Another key property, as I mentioned, synchronous games also have this representation where you can look at their generators as order 2 unitaries. And so we saw that in all the algebras I mentioned, all the generators could be order 2 unitaries. And what happens is that for every epsilon optimal strategy, if I look at the representatives that I get from that strategy, these 5 x's here, they have this interesting property where they almost commute in the Frobenius norm with the square root of the reduced density matrix, and it holds up to this value of epsilon to the 1/4. Now this value actually gets a bit better. I think it's epsilon to the 1/2 in the XOR case, or sorry, in the BCS case. But I'm talking about all of these game algebras here, so I'm going to pick the bound that works. Ooh, I'm at 0 minutes. All right. And so we have, and lastly, it turns out that any epsilon optimal strategy gives me an O epsilon to the 1/4 representation of G with respect to this state-induced norm. So, which is great, but I want to compare my things to maximally entangled states. So what do? Well, my main result is basically that you can do away with with this state dependence. You can round to the little Frobenius norm, and you can just pick up a square root, an extra square root when you do this. So you can go from the rho norm to the little Frobenius norm, which is kind of a more standard norm, and you just pick up this factor here. So we'll obviously skip the point of the proof, and I'll just tell you about the second result here, which basically says that for any epsilon optimal strategy for any of these games, there's an O epsilon of the 1/8 optimal strategy S using a maximally entangled state where all of the measurement operators in this new strategy are close to the measurements in the original one. So I've restricted to some, basically what I've done is I've restricted to some subspace, and on that subspace I can correct all of my measurement, all of the operators that were measurements. I can still make them measurements, and these aren't, so these are still close. And if I play this game with a maximally entangled state on that subspace, I'm still going to be O epsilon of the 1/8 optimal. So if epsilon was really small, then it's saying that I have an epsilon optimal strategy with an arbitrary state. I'm going to be close to one in this kind of sense to one that was using a maximally entangled state. And you can come ask me, where this might go next after this talk, as I'm out of time. So thank you very much.
Question? Hi, thanks for your really interesting talk. What I was wondering about is for your definition of this approximate representations. It seems like the definition depends on your choice of relation on the algebra. Like, is there ever an indication that there's like a best choice of relations to do this with?
Yeah, that's a good point. Yeah, it does. It is sensitive up to presentation.
Mm.
But so yeah, you have to be careful when you change presentations.
Yeah.
There are some results. I think it might just be true though for the operator norm that basically in any presentation you just lose a constant factor of epsilon.
Okay. So,
but I can't recall if it's actually true, if that's true in general. But I think it does happen often when you do have so you have an isomorphism between different presentations. And if you do the math through that, you can kind of make sure that you won't mess things up too much. Like when you go from looking at projections, obviously, to these plus minus one observables, you need to be sure that when you go back and forth between those, that you don't wreck your epsilon representation in the norm you're starting in. So yeah, you do